Hi, we're Group 9 in Computer Modeling and Simulation, and we'll present to you our simulation of a behavior of parking lot. Parking problem is a big problem, especially in metropolitan areas, when there are a lot of vehicles in circulation while the land allocated for parking lots is limited. In Ho Chi Minh City, this problem is arising. Ho Chi Minh City has the largest number of motor vehicles registered in the country with 7.6 million vehicles. And the number of vehicles currently in circulation is already very large, as we have seen, and this number of vehicles will increase in the future. Thus, the infrastructure for the transport system is under increasing pressure. In terms of parking lot, the authority solution why we have more vehicles in circulation is to invest in more parking concentrated projects. However, as cities have parking problems, more parking space is not the solution because the number of land resources is limited. That is why we want to investigate what is the efficient number of parking slots to be built, taking into account the observed arrival rate and parking rate. And here I'll explain to you how the parking lot simulation work. When we begin, the program would initialize parameters, which includes the range of time a person can stay inside a parking lot, the maximum and minimum time between two cars going into the parking lot, and then there's an entity that create more vehicles. When we have initialized the parameters, then the program would calculate the average rate of people going in and going out the parking lot from our collected data. And then it also calculate and set the average process time for someone going in and going out of the parking lot. When the vehicle went into the parking lot, the time of arrival is random using exponential distribution. The program would check if anyone that is already in the process in the queue of going in. If there is no one going in, no one in the queue, then the program would proceed to the taking ticket process, and the processing time of taking ticket process is randomized using exponential distribution. If there is already any vehicle in the queue, then the other vehicle that come after have to wait until the previous vehicle has finished the process, and when the spot is available, then it would proceed to the taking ticket process. Then there's a process for parking space after the vehicles take the ticket. The time for people to find parking space is randomized using exponential distribution. When they find the parking space, the parking time is also randomized by exponential distribution. After they have parked, uh, users would want to take their vehicles out of the parking space, and we have another time for finding the vehicle, which is also randomized using exponential distribution. After they have taken their vehicles and going into the queue that gets the vehicle out, the program once again check if there is anyone already in the queuing process for getting out. If there is an object that is waiting, then the vehicle would have to wait until the previous vehicle has finished the process, and if there's no one in the getting out queue, then they would proceed to the taking ticket process, and these processing time is also randomized using exponential distribution. And then the vehicles would come out and we finish the program.
For our model, we using the exponential distribution to randomize the chance and interval time of people coming in to the parking lot. The time will have the minimum of 20 seconds maximum 30 minutes and the mean of 3 minutes, meaning the minimum would be two people coming in next to each other in 10 seconds. Maximum would be 30-minute interval, and a mean, meaning on average, most people come in 3 minutes from each other. These data are collected in our section of in our sessions, which conclude in an hour and 30 minutes. So it may not be correct. Next is the server. The server here serves as the progress in which we taking ticket to get into the parking lot, and we also use randomized process time, random distribution for it. So because some people would have a faster way of getting the ticket faster. Some people would take ticket slower. Then is the finding parking space, which is a conveyor. This we also use an exponential distribution to randomize the time they can get to a parking space. And lastly, the most important part is the parking lot. This conveyor belt serves as the parking lot, which each NZ has a random distribution of the time where they stay in this parking slot. The average time spent in this parking space has a minimum of 10 minutes, maximum of 24 hours, and a minimum of 2 hours. We limit this thing to only 4 hours so that we can assume that no one would put the bicycle in the parking lot overnight. Then is the taking a vehicle out. We also use random exponential distribution for this to randomize the time people need to find their vehicle. And then there's the queue and server out, which is the time people need to getting the ticket and pay. This is also randomized because some people can pay very fast who ready the money, but sometimes they don't. Speeding up the process, we can use the graph to see the number of vehicle in the parking lot. And as you can see, the graph fluctuates a lot. However, the graph rarely or almost never getting over 60, which is 60 vehicle in the parking lot. So we can safely assume that 60 is the optimized number for this arrival time and this parking lot.
Answering this predictive question would allow us to predict the efficient number of slots and parking space to be built that can serve the demands of people. And the demands of people here is determined by observed arriving and leaving rates. The answer to this question would be very important, especially to developers of the city who would need to answer this question to make sure a parking lot can serve the demands of people by saving land areas. Meanwhile, investors of the system also need the answer to the question to allocate the right amount of money to building parking lot. Answering this question is also interesting because it allows us to predict the range of vehicles in any time period during the day by simulating the driver's arriving and leaving rate, which are observed in reality. Thereby, the developers and investors can know whether the current number of slots and parking space is reasonable. Here, we can learn to determine whether the current parking lot is running on the right amount of resources, but still being able to serve people's changing arriving and leaving rates during the day. Investors can also decide reasonable amount of resources allocated to the project to meet people. both emails.